Recording is rolling. So today I want to do as much AP Classroom Unit 3 as I can. So if you guys haven't finished that yet, so after school today I'll reopen that so you can access that, but can I do that? Now, for that, a couple other things. You guys remember I'm picking up your guys' Chapter 7 homework questions tomorrow. You guys probably already have these finished. Been following along in class. Yeah, maybe you did the bonus too, possibly. Anyways, picking that up tomorrow. Unless you turned it in already, some of you guys have. Okay? And then you guys also have this Open Notes take-home quiz. Looks like this that I'm going to pick up on Monday, and a lot of guys knocked out most or all of that yesterday. So you guys got that too. All right. So before I get to the AP Classroom, though, I've got really a cool starter question for you guys. It involves these O'Neill cylinders. You guys remember O'Neill cylinders, right? So if you're in deep space, there's no real gravity around, not a significant amount. If you create a ring, you give that ring a spin, so you can walk around on the inside as if there is gravity. It's artificial gravity. And so suppose you had a system like this, like two separate O'Neill cylinders, completely independent of each other. So they're not connected in any way. But maybe they're both rotating about the central axis that you create this dash line. So this one's spinning, zoom, zoom, zoom. This one's spinning, zoom, zoom, zoom. And hey, take a look at these inhabitants. They're walking around on the inside of each of those. Suppose they experience the same artificial gravity, and you know the size of the big one compared to the small one. Let's say the big one has 4 times the radial size of the small one, okay, which also means it would have 4 times the diameter. So this diameter is 4 times this diameter. And that also means 4 times the circumference. So if you were to walk all the way around this ring versus all the way around this ring, that's also 4-to-1 ratio. Anything that's a linear proportion, like radius, diameter, circumference, that's all the same proportion. Okay, so the questions, and I have 2. Well, both get almost the same idea, which is, say which one's rotating faster? Actually, you could ask that question, which one's rotating faster? In order for them to all experience the same artificial gravity. So whether you're on the inside or ring or the outside ring, either one, maybe if you close your eyes, it'd be really hard to tell which ring you're on because it just feels the same. Now, they would have to spin at different rates, right? So which one's spinning faster? And thing is, if you say which one's spinning faster, well, you guys know there's 2 different ways to quantify fast. There's the classic way, this way down here, like linear speed, meters per second, miles per hour. But then there's this new way that you guys just learned within the last week or so, which is called angular velocity. You guys remember this? Like how fast is something spinning? Like the Earth makes 1 revolution every 24 hours. That could be like an omega value, something like that. And you can quantify that radians per second. And the way I've couched these questions is, well, what's the ratios of the velocities? What's the ratios of the angular velocities? What's the ratios of the linear speeds? Okay. So this first version is like, if you're watching them spin, how fast one spinning compared to the other. The classic velocity way, like meters per second, is say like, if you're out here floating in space, you point a radar gun at these people, you point a radar gun at these people, and you get like instantaneous speeds. How would those compare? Now, it turns out that, say if I were to ask the question, like which one's rotating faster, you could actually make an argument for either one depending on which type of velocity you were analyzing with. Right? And you might sort of get a hint from that by looking at the equations for centripetal acceleration. You guys remember in your lab a week or 2 back, you guys figured out that centripetal acceleration is, well, centripetal force was mv squared over r, divided by m, it's just centripetal acceleration is v squared over r. Right? That would be the apparent gravity, artificial gravity from motion like this. Right? And if you substitute in v equals omega r, so omega r for that v, and then that should be in your notes too from recently, then you can get this other version of centripetal acceleration, which is also the artificial gravity, which is omega squared times r. So from one perspective, artificial gravity or centripetal acceleration is inversely proportional to radius, but from a different perspective, it's directly proportional. Like, how's that even possible? Right. Well, that's okay because v and omega are related to each other also through the radial size. Okay, so how's this going to play out? If it's a 4-to-1 ratio in terms of radial size, then what's the ratios of these different types of velocities? Okay. Now, we're gonna do this a short way, which is that I've got the notes already. I'm just gonna flash them up here and take you guys through them. Let's start with the angular velocity version. Yeah. All right. And then if this is not enough time to write in your notes, which I don't think it will be, you can check this out on the video too. All right, so I'm gonna start with this. I'm just gonna take this setup here, omega squared r for artificial gravity. I'll create an equation for each one of those O'Neill cylinder rings. Okay? So omega 2 and R2 refer to the big cylinder, omega 1 and R1 refer to the little tiny one. Right? Now, everybody experiences the same artificial gravity, so I'm not even going to throw a subscript on the G. I'm just going to say G, it's equal to this, it's also equal to this. Right? They have different spin rates, they have different radial sizes. In fact, you know the ratio of the radial sizes. That's why I can take this, R2 is 4 times R1, and just sub it in there. Okay. And that's going to look like this, isn't it? So what I put in these curly brackets is think of it sort of like a system of equations, right? We've got two equations, maybe like many unknowns, right? And if you look at it like this, then some things are starting to line up. Like they both have the G in them. They both have the same radial size now, right? R1 and R1. Well, they both have the R1 variable, I should say, right? Okay. But different spin rates. And hey, the question was, what was the ratio of the spin rates, right? This is starting to kind of take that form. In fact, what you can do, you guys remember different ways to solve system of equations. One way you can do it is you can just divide one equation by the other. Okay? And if you do that, you guys see a bunch of stuff's going to cancel out. What's G over G? 1. And then the R1s also cancel. So is that just going to look like this? Is that okay? Okay. And now you're really close to being able to answer this question. Okay. So pretty much done with the physics at this point. You're just doing some algebra at this point. Okay? So divide the 4 over, take the square root. You guys see that? If you divide the 4 over, take the square root. What's the square root of a fourth? A half. Right? Or you could think of it this way. So the small O'Neill cylinder is spinning twice as fast as the big cylinder in terms of angular velocity. Okay? So the inside ring is spinning faster in terms of like numbers, radians per second. So it'll make like 2 revolutions in the same time that it takes the big ring to make 1 revolution. Okay, so it looks like the inside ring is spinning faster, right? Except, wait a minute, faster, there is another way to quantify fast, and that's the way we've been doing it since August, which is like linear speed. So how's that going to work? You guys ready to see that one? Actually, I'll show you guys this one side by side, because it's, except for the starting equations, it's pretty much the same process. Right? So put these side by side. So we did angular velocity, right? Data analysis. Right? Switch over and look at linear velocity. Now this one, I'm playing off this setup, v squared divided by r, which is a lot closer to your guys' centripetal force law. So same idea, I got it for the big ring, v2 squared on r2, and then the little ring, v1 squared on r1. Right? So, but they're both equal to the same centrifugal acceleration, this artificial gravity g. Right? And I'm going to make the same substitution that I did before, which is that r2 is 4 times r1, because we're talking about the exact same O'Neill cylinders, right? Exact same physical setup. So substitute that in, rewrite these equations, wonder what that looks like. Looks like this and this. And remember what I just did a few minutes ago was divide one equation by the other, and a bunch of stuff canceled. You think it's going to be the same thing? That's why I drew these fraction bars in purple ink. I'm taking one equation divided by the other equation. Right? A bunch of stuff cancels, and if you get all that right, it looks like this. So G over G is 1, and then all this stuff works out like this. Cross multiply up to 4, take the square root, and now V2 over V1 is a 2-to-1 ratio. So from a linear velocity perspective, the outside ring is actually moving faster. Like if you're standing on the outside ring, you have a faster linear velocity than on the inside ring. Even though the inside ring has a greater angular velocity. Interesting. Yeah. You guys get that? All right, that's a fun one to digest. So yeah, but got limited time, and I want to do as much of the AP classroom as I can. So I'm gonna switch over and